Welcome to the 14th lecture of class meeting of EECE574, the graduate level probability and random processes. Homework 7 will be assigned before the midterm. And as I announced last time, midterm will be given you as a take-home exam. The problem set will be downloadable from Tuesday during the next class meeting, and it will cover up to that class meeting. You need to submit your solutions by 2 days, within 2 days. Handout for class meeting 5 is just updated, so you need to download it again because some parts and orders are modified. I have a message. Last time I talked about a good practice, and people say that one of a necessary condition for good practice can be said as 3 Fs. What are these? First, focus. Second, feedback, not just feedback, but immediate feedback. And the last one is fix. But about the focus, I need to add something more. As I told you, this 3F is kind of an analogy from our iterative optimization problem. And you remember, in order to solve an optimization problem iteratively, you first need an optimization problem that has an objective function and constraint. Objective function is a measure that measures goodness of your solution. In our user optimization, we usually want to just find the control parameter that gives us some smaller value of objective function. However, when we do physical or mental exercise, we need to set a goal. Not just we need to have a metric. We need to have a goal. Then how can you set a goal? That is today's message. According to the theory, people have researched. They say that every people have his or her comfortable zone in their some practice. However, your new goal or your focus needs to be on little bit uncomfortable zone. For example, every day in the morning, you have hundreds push-ups, and now your muscles have grown and you feel comfortable. Someday, you may say that I need to improve it, but never set a goal like, okay, 1,000 push-ups. You just need slightly yourself to an uncomfortable zone and then achieve. That feeling of achievement really gives you an energy to iterate this practice that ever stop. Okay, so try to set a measurable goal, sometimes time goal. Okay, like you measure the time that requires to solve some problem. So play some note of your music, and you push yourself little bit more. That is one of the methods to achieve a goal. Anyway, let's move on to our overview. So we are almost finishing this chapter 5. So I hope today and next class meeting, we finish reviewing undergraduate part. I have some corrections and clarifications part, but nothing wrong. I need to clarify or add something. Last time, we defined the correlation matrix and the covariance matrix of a random vector. So what was the definition? So given a random variable, we defined the outer product of the vector processed by expectation operator. That is denoted by R sub XX, right? What I want to talk about is some mathematical definition related to this correlation matrix. So first, given a matrix, given a square matrix, given a matrix A that is a real n by n, we call it a positive semi-definite matrix if. So this if part is interesting. So what you do is that you consider some, let me use y transpose a y. What is this one, by the way, when y is also length n vector? This is so-called the quadratic form, right? And this is, if this is always greater than or equal to 0, right? This is scalar R1, and this is scalar 0, right? So if this holds for all vector y, the vector y could be a 0 vector. Obviously, if this vector is a 0 vector, then you have equality. However, in general, when you have a positive semi-definite matrix A, y equals 0 is not always the only vector that makes the equality hold. Okay, sometimes some non-zero vector y can make this equality to hold. Got it? Anyway, a similar definition is this one: positive definiteness given a matrix A that has R rows and R columns. We call it a positive definite matrix if y transpose A y is greater than 0 for all non-zero y. Okay. As I told you, if y is 0, this is always 0. So the positive definiteness means that for every non-zero vector y, the quadratic form is strictly positive. Got it? You see the difference? So semi-definite and definite is different, little bit. Okay. Question: which one implies which one? Of course, if it is positive definite, it is also positive semi-definite. However, the converse is not always true, right? Okay, given that, here goes a very simple lemma. We have defined the correlation matrix over random vector here. So we have some events like this, right? Where I assume X is a real valued n by 1 vector. And can you say something about a correlation matrix in terms of positive definiteness or positive semi-definiteness? If R is a correlation matrix of a random vector, then R is positive semi-definite. Okay. By the way, we introduce a notation like A and 0 matrix, and here some people just use ordinary inequality. Some people say that, well, this is reserved for scalar case. So they love to replace it with some little bit curved inequality. And some people say curvy inequality. Similarly, for the positive definiteness, you use this notation. Be careful. This 0 bold-faced is the n by n all 0 matrix. Okay, be careful. This is not scalar. This is a matrix. Got it? So matrix and matrix is compared. But this curvy inequality does not mean n3 by n3 inequality. It means positive semi-definiteness. Got it? So inequality holds when you, for example, subtract and take the quadratic form. For example, extension of this notation allows us to say something like this. What would be this A curvy inequality greater than or equal to B matrix? Of course, A minus B is a positive semi-definite matrix. Similarly, with this notation, we may have something like this with two square matrices of same size. This means A minus B matrix is a positive definite matrix. Got it? Now, here, I want to use one of these notation to claim some result. What? If R is a correlation matrix of a random vector, R is always positive semi-definite. Okay? And the question is why? Why is it true? So we need a proof. Here we have. We just use the definition. The simplest definition, simplest proof of a lemma is a lemma that uses definition. So here we consider Y transpose RY, which can be rewritten as Y transpose expectation of X vector times X transpose times Y. And now, as you know, this is what? This is a matrix, right? So you can easily see that these two non-random vectors can be moved inside because expectation is a linear operator. So you have expectation of Y transpose X vector, which is random, and X transpose Y. And here we have a trick that this is nothing but what? A scalar, right? This is a scalar. And this is a scalar. And A transpose B is same as B transpose A, right? So you can just square this scalar, and then expectation of a non-negative real random variable is always greater than or equal to 0. So you are done. Got it? You can say the same lemma for a covariance matrix of a random vector. Why? Because covariance matrix is nothing but the correlation matrix of a centered version of the random variable, right? You just subtract the mean and we define capital X minus mu of mu sub X equals Y. Then the covariance matrix of X is simply the correlation matrix of Y. So that's why you have something interesting. Now, what else do we have about the correlation and covariance matrix? They are symmetric matrices. So here goes another lemma you have to remember. Too simple. Correlation matrix of a random vector is symmetrical. Means if you transpose the entries, then you have the same vector. as I just told you, covariance matrix is also a special correlation matrix. So you have this thing. So they are symmetric matrices. Why? If you doubt, again, just use the definition. And the transposition just gives you what? A times B transposed becomes B transpose times A transpose. So you transpose this one, and you transpose that. And you have the same correlation matrix back. So correlation matrix is symmetrical matrix and what? At the same time, positive, semi-definite. Then we have a theorem. Okay? This theorem is not directly related to the correlation or the covariance matrix of a random vector. However, it is, you can find its most usefulness when you apply it to a covariance matrix or a correlation matrix. So here we go. The theorem says that if A, that is an n by n matrix, satisfies 1, it's symmetric, and 2, it is positive semi-definite, then what happens? Related to the eigenvalue decomposition, what do you have? You have very nice decomposition. There exists lambda, that is diag, lambda 1, lambda 2, dot, 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 lambda n, with all non-negative eigenvalues and real and the eigenvectors, and v, that is v1, v2, dot, 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 vn, such that your matrix, positive definite, symmetric positive definite matrix, is well decomposed as v lambda v transpose. And you can rewrite it by using summation I from 1 to n vi lambda I vi transpose. Or if you want, lambda I vi times vi transpose. What does this mean? This condition is satisfied for all correlation and covariance matrices of a random vector, right? And then what does that mean? Your correlation or covariance matrix always allows this so-called, such that V in V transpose V equals I, positive, orthogonal decomposition. Orthogonal eigenvalue decomposition. Actually, orthonormal, because this means that the Vi inner producted with Vj equals 1 if and only if I equals j. Okay, so it's an orthonormal eigen decomposition. So what does that mean? A real random vector has positive semi-definite covariance matrix and correlation matrix that allow orthonormal eigenvalue decomposition. Got it? This is very important for what? When we try to computer generate, especially n-dimensional Gaussian random vector. We will see later. Okay. Here, as you see, we need a technique that relies on eigenvalue decomposition. This is what? This is an orthonormal eigenvalue decomposition of A. Got it? Anyway, so since the lecture note was based on undergraduate course, I didn't talk about this advanced linear algebra material or just linear algebra material in that course in order not to ward off the students from signal processing and communications. But anyway, most of you are already in those labs. It's okay. Okay, so let me have a quick review. Last time we covered some parts of chapter 5, especially related to the expectations. Even though we didn't have this part in the textbook of the undergraduate part, I emphasize the importance of that one, especially after introducing this conditional expectation with point conditioning. I defined this strange thing, strange notation, right? What does this mean? You just call this as a deterministic function of y, and what do? You apply random vector variable y to have a random variable g of y. This g of y is denoted by expectation of x given y when x and y are jointly distributed. Got it? So suppose you have jointly distributed random variables x and y, and you can find the conditional density of x given y. And then using that function of y, you derive y. Then you have a new random variable that is called expectation of x and y. So if you see some of the previous exam problems, the situation is like this, and I ask you to do something. So here, you have a source that generates jointly distributed random variables x and y, and you process y by using this one. Okay. So here you have conditional expectation of x given y, and you have some random variable denoted by x and y. And the question is this: what is the mean of the upper branch output, and what is the mean of the lower branch output? Compute them and compare. What is your answer? That answer is related to this one, total expectation, because expectation of x is simply expectation of this random variable. Okay, got it? They must be jointly distributed. So this type of expectation is called nested expectation or iterated expectation from their shape. However, it is nothing but a special total probability theorem, now which can be called a total expectation theorem. And another thing was this one. So if we have two jointly distributed random variables x and y, what can you say about this conditional expectation? This is what? This is conditional expectation about x, right? So you want to know about x given the observation about y, right? So this is conditional expectation, but at the same time, it is a kind of point estimate of x given jointly distributed random variables realization. And interestingly, in Gaussian case, this is same as the expectation of x with some correction term. And this correction term, of course, relies on the observation y subtracted by its mean. And since this is a unit of y, you need some modification. What kind of modification? You use the variance of y inverse, and then you have a cross correlation between x and y. Then what do you have? These products have the unit of x, right? So if Gaussian, if x and y are jointly Gaussian, then we have these interesting results. But in order to talk about this interesting relation, we needed joint Gaussianity first, right? So first, we introduced a two-dimensional random vector that is called a Gaussian random vector. And interestingly, the PDF was given to define that random variable. And it involved the correlation coefficient and all other second-order moments, right? And then I talked about the special case where two jointly Gaussian random variables are independent. In that case, as we already know, the joint density factors into marginal densities. Another extreme is the degenerate case, where the correlation coefficient is very close to 1 or -1, right? In that case, if you remember the two-dimensional scatter plot, the realized vector x, y shows you some straight line on the R to the 2 plane. What about the conditional density and expectation given two jointly Gaussian random variables? Interestingly, conditional densities were also Gaussian, right? And here, I showed this is correct. And also, I mentioned that this form on the right-hand side, in the lower hand side, right, is what? Something familiar. What is that? It is exactly the best affine approximation of x in terms of y, right? Related to that. For example, you replace this as x hat, and you replace this as y, right? Then you have the best affine approximation of x random variable by using y random variable. So very interesting results. And that result can be extended to n-dimensional case. But n-dimensional case, instead of directly giving the joint PDF, I also have given you the joint characteristic function, because the joint characteristic function does not involve the inverse of the covariance matrix, so that even in degenerate cases, the characteristic function works to fully characterize the Gaussian random vector. However, the density has the determinant of covariance matrix in the denominator, or inverse of the covariance matrix, which is 0 and does not exist when you have a degenerate Gaussian. So I emphasize that the characteristic function is very important when you handle a Gaussian random vector. And we also extended our results and revisited the 2D case as a special case of this n-dimensional case. And also, this conditional mean can be just modified by putting all these underscores to denote that these are vector valued random variables, or vectors. Got it? The last topic we stopped on it was affine transformation of a Gaussian random vector. And I found that our handout had section 5 about the linear transformation of Gaussian random variable, and section 4 for the general transformation of a random vector. So I switched the order of these two, because anyway, we are going to handle this topic first. So let me do that like this. So this is what you've seen last time. This is the characteristic function of a Gaussian random vector. And my question is this. What happens if you transform this Gaussian random vector x to another random vector y, which may have different lengths? So let me see. Okay, length n, and this is length m. Okay. So you want to transform the Gaussian random vector to another random vector, and its length may be different. The simplest transformation is what? Is an affine transformation using a matrix A that is m by n, and vector B that is m by 1. Okay, so matrix A and vector B is given, and I ask you to transform the Gaussian random vector x into some random vector y whose length may be equal or greater or less than the input Gaussian random vector. By the way, as you see here in the complete characterization of a Gaussian random vector, how many parameters do you need to specify the right-hand side? Just mu vector and the covariance matrix, right? So what would be a way to specify the distribution of Gaussian using the mean vector and the covariance matrix? So you have such a notation that simply extends this notation. Okay. This is why people prefer to use variance instead of standard deviation when they have this notation. So x is a Gaussian random variable with mean mu and variance sigma sub x squared, not standard deviation, because when they extend the dimension to multiple, then you cannot easily write something that corresponds to the standard deviation. But this is covariance, and if you just simplify this, consider the extreme case of one dimension, you just simply have covariance matrix of one-dimensional random Gaussian random vector is just the variance of it. Okay, so here I would say that x is Gaussian random vector with mean mu x and covariance matrix C. Okay. So what would be your answer? Affine transformation. And some of you already heard something like this. If we have multiple Gaussian random variables, then their summation is a Gaussian random variable. Probably you've seen that, right? Probably you've heard that. That is actually the special case where A is some row vector. So suppose A is a row vector, that is A transpose. Then what do you have? A transpose X plus now B is a scalar, right? And you have a random variable. This is sigma I from 1 to n. Is it n? Yes. A I x, A I x I. Right? So you have a linear combination that includes the just simple summation as a special case, and plus C that just shifts the distribution. And you know that once this is Gaussian, shift by B is also Gaussian, right? So Probably you heard that result already. So this includes that as special case. But another special case would be something like this. Actually, x is a Gaussian random variable and y is a vector. In that case, you have something like this. So you have a deterministic vector A, and you just multiply a scalar variable x. So you scale, right? And you multiply a B vector. What would it be? So you have some n-dimensional vector A, and its magnitude is multiplied by a single scalar Gaussian. What would be that after you add some B vector? It's a consider n-dimensional scatter plot. You always have a straight line in n dimension. What is that? Actually, that is a degenerate Gaussian random vector. We will see that. Got it? So here goes the proof. Of course, the third case is general case, right? In order to prove the output y is also Gaussian, we just consider the output characteristic function. Okay? So if the output is Gaussian as I claimed, the characteristic function must be in this form with some unknown mean vector of y and some unknown covariance matrix of y, right? Right? So as far as we can find mu sub some parameter mu sub y and cyy that satisfies this equality, right? Not just you find mean and covariance. Okay, that is simple. You need to show that characteristic function can be written by using its mean and covariance matrix of y vector like this. Then it's Gaussian. So we want to show this. And in order to show, we start from the left-hand side. And the left-hand side is simply this one. Let me magnify. Why this is true? Because of the definition. What is that? Expectation of e to the j omega transpose y, right? And what is y? Y is, in this case, I omitted b, but ax plus b. Let me just directly do the, oh, what is, something's wrong. Just a second. Why still it's, oh, okay, got it. I will modify, okay? I love the affine case rather than linear case. So, okay. Here we go. 100%. So the left-hand side equals expectation of e to the j omega y. And in the affine case, we have e to the j, omega transpose ax plus b, right? And this is simply due to the linearity. We have this one. And let me take e to the j omega transpose b out because it's not random, right? This is not random. And it's scalar, right? So I have taken it out. And here I use some trick. I rewrite this one as that. Got it? Omega transpose A is A transpose omega transposed. So what is this then? Anybody? This is the characteristic function of x evaluated at A transpose omega. Why? Because if this is omega tilde, then this is what? Characteristic function of x evaluated at omega tilde. And omega tilde is what? A transpose omega in this case. Got it? Now, what was the characteristic function of x? Exponential j omega tilde transpose mu x minus 1/2 omega tilde transpose the covariance matrix of x omega tilde, where omega tilde is A transpose omega, right? So you have e to the j omega transpose b, e to the j, now what? Omega tilde transpose is omega transpose A transpose. So you have omega transpose A transpose mu x minus 1/2, again, omega transpose A transpose CXX A omega. And what is this one? So we rearrange like this, J omega transpose A, let me see. Oh, no, not transposing. Yeah. A mu x plus B minus 1/2 omega transpose A transpose CXX A omega. So we have successfully arrived at a Gaussian characteristic form. Now, what is this one? Fortunately, we already know that mean of y is simply A times mean of x plus b, and covariance of y is, you can show that it's A transpose covariance of x times A. So we have the story, okay? So this characteristic function method shows that any affine transformation over Gaussian random vector gives us a Gaussian random vector. Whether it is a degenerate Gaussian or not, it doesn't matter. It doesn't matter whether you increase the number of, increase the length of the output vector or reduce the size or have the same length. It doesn't matter. Got it? So this is the proof, which is much general than this linear case. This linear case in the textbook assumes B is a zero vector, right? So it's linear, but let me say this. Any affine transformation over Gaussian random vector gives us a Gaussian random vector. And that proof can be easily done by using the characteristic function. Now, let's move on to section 5.5, which is simply consider a simpler case of linear transformation of Gaussian. And here, it gives some, tries to provide us some sketch, but anyway, this characteristic function method is more straightforward. We are going back to this one again, anyway, because we need to check the Jacobian trick. Okay, so we move back to section 5.4, where we consider general transformation of a random vector to another random vector. So let me draw the same figure again. So here you have a random vector x, and here you have some mapping that gives you a random vector y. For this, we have something like this, g of x. And let me use underline here to mean that this is a deterministic vector valued function of a vector x. So actually, this g can be written in this form, g1 of x, g2 of x. For consistency, let's consider, was it m? Let me see. Okay, n, x is length n. So this is length n vector, random vector. This is length m vector. So we have how many outputs do we have? Capital M. So you have up to g sub capital M of x. So you have capital M deterministic functions that maps a vector into scalar. So you have M scalars and what? As we already know, here we have what? We have an underlying probability space and some set of measurable functions that generates random vector x. Now what we do is that we put a box here, and what happens? We have an underlying probability space that describes the random experiment, and its outcome S derives this new measurable function. So output is a random vector again. So Y is definitely a random vector, and what would be our question? Characterize Y. Without talking about anything in terms of course, the distribution of X, and of course, the mapping rule, G. So how can you do this? And we've seen this already, actually, when m equals 1 and n equals 1. In that case, we had what? We had a random variable x and a deterministic function g, and we had a random variable y. In this case, right? In this case, what did we have? What did we have? We had some result like this. First, we try to find the CDF of y in terms of CDF of x. Right? But unfortunately, this G inverse of y does not give you some nice, very simple single valued function. So you need to do something here. But anyway, in principle, you can find the CDF of the output, and then you can find the PDF of that. What was the second method? Second method called Jacobi's method. And it gave us directly the density function of the output, but it was something like this. So given y, we may have multiple values of x, and that is denoted by x sub I of y. And what we do is that we first evaluate the density of x at the corresponding value of xi, and then divide by the absolute value of the derivative of the mapping rule at that point of x. And This also has the special case, simplified special case, and the special case occurs what? When G is affine. Probably you remember when G equals AX plus B, then you have absolute value of A here, and this corresponds to that A, okay? Now, what can we say? What can we say for M greater than 1 and N greater than 1? Can we do something similar to that? Always. However, it's complicated. What about this Jacobi's method? How can we extend that idea to multidimensional case? And in order to approach this special case, we again consider simplification. So the simplification goes like this. Let me give you some idea. No, too simple. Okay, let me see. Yeah. So what we do is that we consider the simplest case of n-dimensional to n-dimensional case. Got it? Because that gives us simpler idea. N-dimensional, n-dimension to n-dimension. So input and output have the same length. And then let's try to understand or derive the result in that case. So here again, we have simplification where m equals n. Then we have something like this. x1, x2, dot, 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 xn goes in, and y1, y2, dot, 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 yn, which is simply y vector, goes out, comes out, right? What would be the result? Again, we consider simplified case. That is something like this. We have y1 equals some g1 of x1. Yn equals gn of xn. So we have individual functions that maps x sub I into y sub I. That would be the simplest case, right? Then what do we have? Then what do we have? Still it's complicated. Now let me ask you again. What if xi's are independent? So it's like you just simplify and simplify until you get the simplest case. What do you have? So in this case, you have something like this, right? Now, each individual density is mapped by G sub I. And we can apply this result, right? So definitely you have something like this. That would be we need a summation, sorry. J, let me use. And this one look like that. Notation is complicated. But you know what I mean, right? What I want to say. And this is something similar like this. Y. Right. And this is the product of these derivatives. And you can say that this is something like that. By the way, what is the determinant of a diagonal matrix? It's the product of the entries, as you know, right? So here, this product can be rewritten in this form, right? The reason why I do this is that we already know the result, right? Yeah. So suddenly, you come to understand this generalization. So here goes our result. That is too sudden, but let me give you. The output density has almost the same form as our one-dimensional case when we now have n-dimension to n-dimension mapping. Oh, sorry. So here we have not that one yet. One, two, n. Now, just a second. One, and one. Okay. Yeah, something like this. By the way, what is this one? What is this one? So in each row, you have the first function's partial derivatives, second function's partial derivatives with respect to x1, x2, and xn. And so does partial derivative. And this is what? This is, in the special case of that separable mapping, it reduces to what? The derivatives on the diagonals. Okay. So if they are not simply that separable functions, you have this one. By the way, let me ask you a question. What if we have an affine mapping? Actually, this is nothing but the matrix A. Why? Consider that A has A11, A12, A13, right? And the first function is simply A11 times x1 plus A12 times x2 plus something like that. So if you can compute this derivative on the first row, you have the first row of A matrix. Got it? So actually, this is nothing but that one if you generalize. So as I told you last time, for the one-dimensional case, what was our density? When A is non-zero. We had something like this, right? We again and again and again and again recall this result because this is the simplest one and easy to remember. And this generalizes to any case. Okay? And as you see, this A is now has become matrix A. And if you're an affine transformation, you just have what here? The determinant of this A matrix. What if you don't have affine mapping? Still, locally, any function that is smooth can be well approximated by an affine function, right? That is the theory of calculus, differential calculus, right? If the function is smooth enough so that we have partial derivatives, we can approximate any function locally by using an affine function. So this is not strange, something strange. This is okay, perfectly okay, right? So link the simplest result from one dimension to one dimension mapping, and you extend it to an affine mapping of n dimension to n dimension. Here, x and y have same length, and then you generalize to arbitrary nonlinear mapping. Okay? Be careful, you sometimes have multiple terms on the right-hand side, not always a single term. But usually we transform to another random variable by using a one-to-one correspondence. That is good. Okay? In that case, we have a single summation, so single term, so summation drops off. Got it? Anyway, so we are happy now that we can just get a result from n-dimensional random vector to n-dimensional random vector case. But what if we have different lengths? What do we do? Here goes some trick that could be working or sometimes not working. So suppose x is shorter than y. So x is this size, y is that size. No. The reverse first. Y is short. What do we do? Actually, it's very simple. What we do is that we consider some z that contains all y's and 0 vectors to make the length of z the same as the length of x, right? Because this is what? Z equals now what? Some g of x and here 0, which is what? This is again special affine mapping with 0 matrix A, 0 vector B. No problem. So this is a big n by n mapping, n dimension from n dimension mapping. So theoretically, you can find the density function of z. Now from this, how can you get the density function of y? By marginalization. In theory, right? You marginalize, which means that you remove the last lower part. Let me call it z sub 2 vector, right? By integrating over these variables, then you are done. So when the size reduces, no problem. What if the size increases? Again, you can pad zeros to the x, right? And you may call it as w, and you consider transformation from w to y. And arbitrary value of that lower part of w doesn't matter, right? But in general, you have a degenerate random vector as the output, as you can easily guess, right? As we've seen already, consider you have just scalar x Gaussian, and the output is the product of that scalar with a deterministic vector plus some deterministic vector. Then you have a single vector whose magnitude or amplitude is proportional to that generated Gaussian random variable. Anyway, so here goes the terminologies. Whenever you have a transformation, not necessarily, yeah, necessarily here, the same dimension. That's the transformation as t, okay? Unlike my g underscore. Then what? This partial derivative matrix is called the Jacobian matrix, Jacob's matrix, okay? And this Jacobian matrix has determinant. That is called the Jacobian determinant. But be careful. In our Jacobi's method, we need to take the absolute value of that determinant. Got it? As we've done for the one dimension to one dimension affine transformation, right? Otherwise, sometimes your density locally becomes negative. It doesn't make sense, right? Your density has come from, PDF has come from the histogram that never goes below 0. Anyway, some people say Jacobian to denote Jacobian determinant. It's confusing. So I usually say that Jacobian matrix, Jacobian determinant, not just Jacobian, because I don't even know which one I denote. So, okay, anyway, so Jacobian matrix is, of course, a matrix. Determinant, Jacobian determinant is also a matrix determinant, but in general, it's a function, right? It's a scalar valued function of a vector. Be careful. Anyway, so here goes our result when the transformation is invertible, which means that 1-to-1, it has 1-to-1 correspondence. So as you see that density of output is simply density of input divided by the absolute value of the Jacobian determinant evaluated at that x. Got it? Very simple. And actually, this result comes from multivariate calculus, as you know. So left-hand side is the probability of an event in the x space. And this is the probability of event in the y space, where these two events are equivalent. And you see why you have this result. So you multiply this denominator to the both sides, and then you have the result. And that is similar to the Cartesian to polar transformation, polar to Cartesian transformation, and blah, blah, blah. But whenever you have confusion, just consider affine transformation. Just consider the simplest affine transformation, which has diagonal matrix. Then you can easily understand what you missed and what you forgot. Got it? Okay, we have the the last topic, computer generation of multiple random variables. So let's review what we've done for a single random variable. What was the key idea? We wanted to generate a random variable, single random variable. We wanted to have a random number generator. And for arbitrary random variable, we need some arbitrary generator. We didn't like that idea. So what we've done is that we had the uniform random number generator that ranges from 0 to 1. And then converted the question like this. Given a uniform pseudo-random number generator by computer or some quantum physical source, then what kind of deterministic function can give you your desired distribution? And that was very interesting. So you have some histogram, right? After normalization, this is the density of U random variable. And what you do is that you generate some number from x to y. And here goes something interesting. Here you have for example, the inverse of the CDF over random variable that has continuous CDF, for example. Then, interestingly, you can show that you have the output, let's say output V, that follows the density of X, right? And we wanted to generalize this one for discontinuous CDF that has jump discontinuity. So we redefined this function as a percentile function, no longer just the inverse of the CDF because it may not exist. So percentile function. So if we redefine that notation as a percentile function, we are done for any random variable. So we are happy. The problem is this. What if we want to generate a Gaussian random variable, single Gaussian random variable? We need the inverse function of the Gaussian CDF. And even not the inverse, just the Gaussian CDF does not have a closed form. What do we do? Of course, most of the commercial software package has what? The CDF and inverse CDF even as a function. We may use that. But interesting thing is like this. As we've just seen, even though we just want to generate a single random variable, what if we generate two jointly Gaussian random variables, x and y, and just drop y to have a Gaussian x? Maybe okay, right? So what we do is this first. We first generate two IID standard Gaussian random variables by using uniform random number generator twice. So what does that mean? Actually, we have independent U1 and U2 that are both uniform from 0 to 1. Got it? And interestingly, from the idea borrowed from the communication theory or actually physics, Rayleigh showed that this x and y can be written very interestingly like this. See that? Let me use some different notation because this is so confusing. Let me say x1 equals square root 2 negative 2 log u1 cosine 2 pi u2. And let me see. Yeah, x2 equals negative 2 log u1 sine 2 pi u2. Got it? So u1 and u2 are uniform random variables. And this cosine and sine and logarithmic functions are called elementary functions. So without relying on that complicated Gaussian CDF or its inverse or its percentile function, we can easily generate two independent Gaussian random variables very easily. And actually, you can show this, okay? Then what do? You just drop x2, done. Or if you want to generate two Gaussian random variables, just generate in this way. Now, let me ask you a question. Can you generate n IID Gaussian random variables for any n? Yes, you can. What do? If n is odd, just generate one more Gaussian independent and drop that. You use U1, U2, U3, UN plus 1 and group these two to generate x1 and x2 pair, x3 and x4 pair, something like that. So now you know that it's not that difficult to generate any n IID Gaussian random variables with 0 mean and variance 1, right? And now let's generalize this one to the case where we want to generate two correlated Gaussian random variables and correlated Gaussian random variables. What do? The idea is simple, actually. We use the eigenvalue decomposition idea. So suppose that we want to generate mean mu x covariance CXX Gaussian random, let me use y, okay? Y, okay? From x that is Gaussian, 0 mean, and unit variance, IID, okay? What do? Interestingly, y can be generated this way. You find so-called the square root of the covariance matrix of your desired output. multiply x and add your desired mean. You are done. Here, this is the theorem. CYY square root equals V lambda square root inverse V transpose. Again, where lambda square root inverse equals 1 over lambda 1 dot 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 1 over lambda n. If x is an n-dimensional, y is n-dimensional. So as far as you can generate a standard Gaussian IID, then this transformation always gives you your desired Gaussian random vector y. Not only the two-dimensional case, which is special case, for any n-dimensional case, as far as here, as far as your desired output has positive definite covariance matrix. Because here we have the inverse of the eigenvalue, right? So they must be all positive. Another one is, this is theorem 2, is that you just need to factorize the desired covariance matrix using lower and upper triangular matrices by using so-called Cholesky factorization. And then, especially you can do something like this, lower transpose. And then you use the lower triangular matrix to generate the y and add the desired mean. This is the second method. So there are two methods. First one that relies on eigenvalue decomposition. Second method that relies on the Cholesky factorization of your desired covariance matrix. Okay, something's not correct. Let me do this. Just a second, just this. Yeah. So covariance inverse. No. Something's not correct. Okay. Yeah, this may be correct. Then let me see. Okay, you don't need the inverse of it then. Just a sec. Yeah, you don't need that. Let me correct. So this part is wrong. You just need to need a square root. Okay. But anyway, so here you don't need the positive definiteness. This can be positive semi-definite. Okay, I've mistaken. Okay, so this one or that one works for any Gaussian random vector. So as far as you can generate IID Gaussian random variables. So we've covered up to half of the story, and next time we will cover the last part, and then we take the exam, and then we move on to the final topic of the random process. That starts with the random sequence and convergence concepts. That's all for today.